Welcome to Data Science, an Introduction. I'm Barton Poulsen, and what we're going to do in this course is we're going to have a brief, accessible, and non-technical overview of the field of data science. Now, some people, when they hear data science, they start thinking things like data and think about piles of equations and numbers, and then to throw on top of that science, and think about people working in their lab, and they start to say, that's not for me. I'm not really a technical person, and that just seems much too techy. Well, here's the important thing to know. While a lot of people get really fired up about the technical aspects of data science, the important thing is that data science is not so much a technical discipline, but creative. And really, that's true. The reason I say that is because in data science, you use tools that come from coding and statistics and from math, but you use those to work creatively with data. The idea is that there's always more than one way to solve a problem or answer a question, or most importantly, to get insight, because the goal, no matter how you go about it, is to get insight from your data. And what makes data science unique compared to so many other things is that you try to listen to all of your data, even when it doesn't fit in easily with your standard approaches and paradigms. You're trying to be much more inclusive in your analysis. And the reason you want to do that is because everything signifies, everything carries meaning, and everything can give you additional understanding and insight into what's going on around you. And so in this course, what we're trying to do is give you a map to the field of data science and how you can use it. And so now you have the map in your hands and you can get ready to get going with data science. Welcome back to Data Science and Introduction, and we're going to begin this course by defining data science. That makes sense, but we're going to do it in kind of a funny way. The first thing I'm going to talk about is the demand for data science. So let's take a quick look. Now, data science can be defined in a few ways. I'm going to give you some short definitions. Take one on my definition is that data science is coding, math, and statistics in applied settings. That's a reasonable working definition. But if you want to be a little more concise, I've got take two on a definition that data science is the analysis of diverse data or data that you didn't think would fit into standard analytic approaches. A third way to think about it is that data science is inclusive analysis. It includes all of the data, all of the information that you have in order to get the most insightful and compelling answer to your research questions. Now, you may say to yourself, wait, that's it? Well, if you're not impressed, let me show you a few things. First off, let's take a look at this article. This says, Data Scientists, the sexiest job of the 21st century. And please note that this is coming from Harvard Business Review. So this is an authoritative source, and it's the official source of this saying that data science is sexy. Now, again, you may be saying to yourself, sexy? I hardly think so. Well, oh yeah, it's sexy. And the reason data science is sexy is because first, it has rare qualities, and second, it has high demand. Let me say a little more about those. The rare qualities are that data science takes unstructured data, then finds order, meaning, and value in the data. Those are important, but they're not easy to come across. Second, high demand. Well, the reason it's in high demand is because data science provides insight into what's going on around you, and critically, it provides competitive advantage, which is a huge thing in business settings. Now, let me go back and say a little more about demand. Let's take a look at a few other sources. So for instance, the McKinsey Global Institute published a very well-known paper, and you can get at it with this URL. And if you go to that webpage, this is what's going to come up. And we're going to take a quick look at this one, the executive summary. It's a PDF that you can download. And if you open that up, you'll find this page. And let's take a look at the bottom right corner. Two numbers here. I'm going to zoom in on those. The first one is they are projecting a need in the next few years for somewhere between 140 and 190,000 deep analytical talent positions. So this means actual practicing data scientists. That's a huge number. But almost 10 times as high is 1.5 million more data savvy managers will be needed to take full advantage of big data in the United States. Now, that's people who aren't necessarily doing the analysis, but have to understand it, who have to speak data. And that's one of the main purposes of this particular course, is to help people who may or may not be the practicing data scientists learn to understand what they can get out of data and some of the methods used to get there. Let's take a look at another article from LinkedIn. Here's a shortcut URL for it. And that'll bring you to this webpage, the 25 hottest job skills that got people hired in 2014. And take a look at number 1 here, statistical analysis and data mining, very closely related to data science. And just to be clear, this was number 1 in Australia, in Brazil, in Canada, in France, in India, in the Netherlands, in South Africa, in the United Arab Emirates, in the United Kingdom, everywhere. And if you need a little more, let's take a look at Glassdoor, which published an article this year, 2016, and it's about the 25 best jobs in America. And look at number 1 right here. It's data scientist. And we can zoom in on this information. It says there's going to be 1,700 job openings with a median base salary of over $116,000 and fabulous career opportunities and job scores. So if you want to take all of this together, the conclusion you can reach is that data science pays. And I can show you a little more about that. So for instance, here's a list of the top 10 highest paying salaries that I got from US News. We have physicians or doctors, dentists, and lawyers, and so on. Now, if we add data scientists to this list using data from O'Reilly.com, we have to push things around the side, and it goes in third with an average total salary, not the base that we had in the other one, but the total compensation of about $144,000 a year. That's extraordinary. So, in sum, what do we get from all of this? First off, we learn that there is a very high demand for data science. Second, we learn that there's a critical need for both specialists, those are the sort of practicing data scientists, and for generalists, people who speak the language and know what can be done. And of course, there's excellent pay. And altogether, this makes data science a compelling career alternative and a way of making you better at whatever you're doing. Back here in data science, we're going to continue our attempt to define data science by looking at something that's really well known in the field, the data science Venn diagram. Now, if you want to, you can think of this in terms of what are the ingredients of data science. Well, we're going to first say thanks to Drew Conway, the guy who came up with this. And if you want to see the original article, you can go to this address. But what Drew said is that data science is made of 3 things, and we can put them as overlapping circles because it's the intersection that's important. Here on the top left is coding or computer programming, or as he calls it, hacking. On the top right is stats, or stats in mathematics, or quantitative abilities in general. And on the bottom is domain expertise, or intimate familiarity with a particular field of practice, business or health or education or something like that. And the intersection here in the middle, that is data science. So it's the combination of coding and statistics in math and domain knowledge. Now let's say a little more about coding. The reason coding is important is because it helps you gather and prepare the data, because a lot of the data comes from novel sources and it's not necessarily ready for you to gather, and it can be in very unusual formats. And so coding is important because it can require some real creativity to get the data from these sources to put it into your analysis. Now, a few kinds of coding that are important. For instance, there's statistical coding. A couple of major languages in this are R and Python, 2 open source free programming languages. R specifically for data, Python's general purpose, but well adapted to data. The ability to work with databases is important too. The most common language there is SQL, usually pronounced SQL, which stands for Structured Query Language, because that's where the data is. Also, there's the command line interface, or if you're on a Mac, people just call it the terminal. The most common language there is Bash, which actually stands for Born Again Shell. And then searching is important, and regex, or regular expressions, while there's not a huge amount to learn there, it's a small little field. It's sort of like super powered wildcard searching that makes it possible for you to both find the data and reformat it in ways that are going to be helpful for your analysis. Now let's say a few things about the math. You're going to need things like a little bit of probability, some algebra, of course, regression, very common statistical procedure. Those things are important. And the reason you need the math is because that's going to help you choose the appropriate procedures to answer the question with the data that you have. And probably even more importantly, it's going to help you diagnose problems when things don't go as expected. And given that you're trying to do new things with new data in new ways, you're probably going to come across problems. And so the ability to understand the mechanics of what's going on is going to give you a big advantage. And the third element of the data science Venn diagram is some sort of domain expertise. Think of it as expertise in the field that you're in. Business settings are common. You need to know about the goals of that field, the methods that are used, the constraints that people come across. And it's important because whatever your results are, you need to be able to implement them well. Data science is very practical and it's designed to accomplish something, and your familiarity with a particular field of practice is going to make it that much easier and more impactful when you implement the results of your analysis. Now let's go back to our Venn diagram here just for a moment. Because this is a Venn, we also have these intersections of two circles at a time. At the top is machine learning. At the bottom right is traditional research. And on the bottom left is what Drew Conway called the danger zone. Let me talk about each of these. First off, machine learning, or ML. Now you think about machine learning, and the idea here is that it represents coding or statistical programming and mathematics without any real domain expertise. Sometimes these are referred to as black box models. They kind of throw data in, and you don't even necessarily have to know what it means or what language it's in, and it'll just kind of crunch through it all, and it'll give you some regularities. That can be very helpful, but machine learning is considered slightly different from data science because it doesn't involve the particular applications in a specific domain. Also, there's traditional research. This is where you have math or statistics and you have domain knowledge, often very intensive domain knowledge, but without the coding or programming. Now, you can get away with that because the data that you use in traditional research is highly structured. It comes in rows and columns, is typically complete, and is typically ready for analysis. Doesn't mean your life is easy, because now you have to expend an enormous amount of effort in the method in designing the project and in the interpretation of the data. So still very heavy intellectual cognitive work, but it comes in a different place. And then finally, there's what Conway called the danger zone. And that's the intersection of coding and domain knowledge, but without math or statistics. Now, he says it's unlikely to happen, and that's probably true. On the other hand, I can think of some common examples what are called word counts, where you take a large document or a series of documents and you count how often each word appears in there. That can actually tell you some important things. And also drawing maps and showing how things change across place and maybe across time. You don't necessarily have to have the math, but it can be very insightful and helpful. So let's think about a couple of backgrounds where people come from here. First is coding. You can have people who are coders who can do math, stats, and business. So you get the three things, and this is probably the most common. Most of the people come from a programming background. On the other hand, there's also stats or statistics, and you can get statisticians who can code and who also can do business. That's less common, but it does happen. And finally, there's people who come into data science from a particular domain. These are, for instance, business people who can code and do numbers, and they're the least common, but all of these are important to data science. And so in sum, here's what we can take away. First, several fields make up data science. Second, diverse skills and backgrounds are important and they're needed in data science. And third, there are many roles involved because there's a lot of different things that need to happen. We'll say more about that in our next movie. The next step in our data science introduction and our definition of data science is to talk about the data science pathway. So I like to think of this as when you're working on a major project, you got to do one step at a time to get from here to there. In data science, you can take the various steps and you can put them into a couple of general categories. First, there are the steps that involve planning. Second, there's the data prep. Third, there's the actual modeling of the data. And fourth, there's the follow-up. And there are several steps within each of these. I'll explain each of them briefly. First, let's talk about planning. The first thing you need to do is you need to define the goals of your project so you know how to use your resources well, and also so you know when you're done. Second, you need to organize your resources. So you might have data from several different sources. You might have different software packages. You might have different people, which gets us to the third one. You need to coordinate the people so they can work together productively. If you're doing a handoff, it needs to be clear who's going to do what and how their work is going to go together. And then, really to state the obvious, you need to schedule the project so things can move along smoothly and you can finish in a reasonable amount of time. Next is the data prep, where you're taking like food prep and getting the raw ingredients ready. First, of course, is you need to get the data, and it can come from many different sources and be in many different formats. You need to clean the data, and the sad thing is this tends to be a very large part of any data science project, and that's because you're bringing in unusual data from a lot of different places. You also want to explore the data. That is, really see what it looks like, how many people are in each group, what the shape of the distributions are like, what's associated with what. And you may need to refine the data, and that means choosing variables to include, choosing cases to include or exclude, making any transformations to the data you need to do. And of course, these steps kind of can bounce back and forth from one to the other. The third group is modeling or statistical modeling. This is where you actually want to create the statistical model. So for instance, you might do a regression analysis or you might do a neural network. But whatever you do, once you create your model, you have to validate the model. You might do that with holdout validation. You might do it really with a very small replication if you can. You also need to evaluate the model. So once you know that the model is accurate, what does it actually mean and how much does it tell you? And then finally, you need to refine the model. So for instance, there may be variables you want to throw out. There may be additional ones you want to include. You may want to, again, transform some of the data. You may want to get it so it's easier to interpret and apply. And that gets us to the last part of the data science pathway, and that's follow-up. And once you've created your model, you need to present the model because it's usually work that's being done for a client. Could be in-house, could be a third party, but you need to take the insights that you got and share them in a meaningful way with other people. You also need to deploy the model. It's usually being done in order to accomplish something. So for instance, if you're working with an e-commerce site, you may be developing a recommendation engine that says people who bought this and this might buy this. You need to actually stick it on the website and see if it works the way you expected it to. Then you need to revisit the model because a lot of times the data that you worked on is not necessarily all of the data, and things can change when you get out in the real world, or things just change over time. And so you have to see how well your model is working. And then just to be thorough, you need to archive the assets, document what you have, and make it possible for you or for others to repeat the analysis or develop off of it in the future. So those are the general steps of what I consider the data science pathway. And in sum, what we get from this is three things. First, data science isn't just a technical field. It's not just coding. Things like planning and presenting and implementing are just as important. Also, contextual skills, knowing how it works in a particular field, knowing how it will be implemented, those skills matter as well. And then, as you got from this whole thing, there's a lot of things to do, and if you go one step at a time, there'll be less backtracking, and you'll ultimately be more productive in your data science projects. We'll continue our definition of data science by looking at the roles that are involved in data science, the way that different people can contribute to it. That's because it tends to be a collaborative thing, and it's nice to be able to say that we're all together, working together towards a single goal. So let's talk about some of the roles involved in data science and how they contribute to the projects. First off, let's take a look at engineers. These are people who focus on the back-end hardware, for instance, the servers and the software that runs them. This is what makes data science possible, and it includes people like developers, software developers, or database administrators, and they provide the foundation for the rest of the work. Next, you can also have people who are big data specialists. These are people who focus on computer science and mathematics, and they may do machine learning algorithms as a way of processing very large amounts of data. And they often create what are called data products. So a thing that tells you what restaurant to go to, or that says you might know these friends, or provides ways of linking up photos. Those are data products, and those often involve a huge amount of very technical work behind them. There are also researchers. These are people who focus on domain-specific research. So for instance, physics or genetics or whatever. And these people tend to have very strong statistics, and they can use some of the procedures and some of the data that comes from the other people, like the big data researchers, but they focus on these specific questions. Also, in the data science realm, you'll find analysts. These are people who focus on the day-to-day tasks of running a business. So for instance, they might do web analytics like Google Analytics, or they might pull data from a SQL database. And this information is very important and good for business. And so analysts are key to the day-to-day functioning of business, but they may not exactly be data science proper, because most of the data they're working with is going to be pretty structured. Nevertheless, they play a critical role in business in general. And then, speaking of business, you have the actual business people, the men and women who organize and run businesses. These people need to be able to frame business relevant questions that can be answered with the data. Also, the business person manages the project and the efforts and the resources of others. And while they may not actually be doing the coding, they must speak data. They must know how the data works, what it can answer, and how to implement it. You can also have entrepreneurs. So you might have, for instance, a data startup. They're starting their own little social network or their own little web search platform. An entrepreneur needs data and business skills, and truthfully, they have to be creative at every step along the way, usually because they're doing it all themselves at a smaller scale. Then we have in data science something known as the full stack unicorn. And this is a person who can do everything at an expert level. And they're called a unicorn because truthfully, they may not actually exist. I'll have more to say about that later. But for right now, we can sum up what we got out of this video by three things. Number one, data science is diverse. There's a lot of different people who go into it, and they have different goals for their work, and they bring in different skills and different experiences and different approaches. Also, they tend to work in very different contexts. An entrepreneur works in a very different place from a business manager, works in a very different place from an academic researcher, but all of them are connected in some way to data science and make it a richer field. The last thing I want to say in data science and introduction, where I'm trying to define data science, is to talk about teams in data science. The idea here is that data science has many different tools, and different people are going to be experts in each one of them. Now, you have, for instance, coding, and you have statistics. Also, you have fields like design or business and management that are involved. And the question, of course, is who can do all of it? Who's able to do all of these things at the level that we need? Well, that's where we get this saying. I've mentioned it before. It's the unicorn. And just like in ancient history, the unicorn is a mythical creature with magical abilities. In data science, it works a little differently. It is a mythical data scientist with universal abilities. The trouble is, as we know from the real world, there's really no unicorns animals, and there's really not many unicorns in data science. Really, there's just people. And so we have to find out how we can do the projects, even though we don't have this one person who can do everything for everybody. So let's take a hypothetical case just for a moment. I'm going to give you some fictional people. Here is my fictional person, Otto, who has strong visualization skills, who has good coding, but has limited analytics or statistical ability. And if we graph his stuff out, his abilities, so here we got 5 things that we need to have happen. And for the project to work, they all have to happen at least a level of 8 on the 0 to 10. If we take his coding ability, well, he's almost there. Statistics, not quite, halfway. Graphics, yes, he can do that. And then business, all right. And project, pretty good. So what you can see here is in only one of these 5 areas is Otto sufficient on his own. On the other hand, let's pair him up with somebody else. Let's take a look at Lucy. And Lucy has strong business training, has good tech skills, but has limited graphics. And so if we get her profile on the same thing that we saw, there's coding, pretty good. Statistics, pretty good. Graphics, not so much. Business, good. And projects, okay. Now, the important thing here is that we can make a team. So let's take our 2 fictional people, Otto and Lucy, and we can put together their abilities. Now, I actually have to change the scale here a little bit to accommodate the both of them, but our criterion still is at 8. We need a level of 8 in order to do the project competently. And if we combine them, oh look, coding's now past 8. Statistics is past 8. Graphics is way past. Business, way past. And then the projects, there too. And so when we combine their skills, we are able to get the level that we need for everything. Or to put it another way, we have now created a unicorn by team. And that makes it possible to do the data science project. So in sum, you usually can't do data science on your own. That's a very rare individual. Or more specifically, people need people. And in data science, you have the opportunity to take several people and make collective unicorns so you can get the insight that you need in your project and you can get the things done that you want. In order to get a better understanding of data science, it can be helpful to look at contrasts between data science and other fields. Probably the most informative is with big data, because these 2 terms are actually often confused. It makes me think of situations where you have 2 things that are very similar, but not the same, like we have here in the Piazza San Carlo in Turin, Italy. Part of the problem stems from the fact that data science and big data both have Venn diagrams associated with them. So for instance, Venn number 1 for data science is something we've seen already. We have 3 circles. And we have coding, and we have math, and we have some domain expertise that put together get data science. On the other hand, Venn diagram number 2 is for big data. It also has 3 circles, and we have the high volume of data, the rapid velocity of data, and the extreme variety of data. Take those 3 V's together, you get big data. Now, we can also combine these 2 if we want in a third Venn diagram we call big data and data science. This time it's just 2 circles with big data on the left and data science on the right. And the intersection there in the middle is big data science, which actually is a real term. But if you want to do a compare and contrast, it kind of helps to look at how you can have one without the other. So let's start by looking at big data without data science. So these are situations where you may have the volume or velocity of variety data, but don't need all the tools of data science. So we're just looking at the left side of the equation right now. Now, truthfully, this only works if you have big data without all 3 V's. Some say you have to have the volume, velocity, and variety for it to count as big data. I basically say anything that doesn't fit into a standard machine is probably big data. I can think of a couple of examples here of things that might count as big data, but maybe don't count as data science. Machine learning, where you can have very large data sets and probably very complex, doesn't require much domain expertise, so that may not be data science. Word counts, where you have an enormous amount of data, and it's actually a pretty simple analysis. Again, doesn't require much sophistication in terms of quantitative skills or even domain expertise. So maybe not data science. On the other hand, to do any of these, you're going to need to have at least 2 skills. You're going to need to have the coding, and you will probably have to have some sort of quantitative skills as well. So how about data science without big data? That's the right side of this diagram. Well, to make that happen, you're probably talking about data with just one of the three V's from big data. So either volume or velocity or variety, but singly. So for instance, genetics data, you have a huge amount of data and it comes in a very set structure and it tends to come in at once. So you got a lot of volume and it's a very challenging thing to work with. You have to use data science, but it may or may not count as big data. Similarly, streaming sensor data, where you have data coming in very quickly, but you're not necessarily saving it. You're just looking at these windows in it. That's a lot of velocity and it's difficult to deal with. It takes data science, the full skill set, but it may not require big data per se. Or facial recognition, where you have enormous variety in the data because you're getting photos or videos that are coming in. Again, very difficult to deal with, requires a lot of ingenuity and creativity, may or may not count as big data depending on how much of a stickler you are about definitions. Now, if you want to combine the two, we can talk about big data science. And in that case, we're looking right here at the middle. This is a situation where you have volume and velocity and variety in your data. And truthfully, if you have the three of those, you are going to need the full data science skill set. You're going to need coding and statistics and math, and you're going to have domain expertise, primarily because of the variety you're dealing with. But taken all together, you do have to have all of it. So in sum, here's what we get. Big data is not identical to data science. Now there's common ground, and a lot of people who are good at big data are good at data science and vice versa, but they are conceptually distinct. On the other hand, there is the shared middle ground of big data science that unifies the two separate fields. Another important contrast you can make in trying to understand data science is to compare it with coding or computer programming. Now, this is where you're trying to work with a machine and you're trying to talk to that machine to get it to do things. In one sense, you can think of coding as just giving task instructions, how to do something, and it's a lot like a recipe when you're cooking. You get some sort of user input or other input, and then maybe you have if-then logic and you get output from it. To take an extremely simple example, if you're programming in Python version 2, you write print and then in quotes, hello world, and that will put the words hello world on the screen. So you gave it some instructions and it gave you some output. Very simple programming. Now, coding and data gets a little more complicated. So for instance, there's word counts where you take a book or a whole collection of books, you take the words and you count how many there are in there. Now, this is a conceptually simple task, and domain expertise and really math and statistics are not vital, but to make valid inferences and generalizations in the face of variability and uncertainty in the data, you need statistics. And by extension, you need data science. It might help to compare the two by looking at the tools of the respective trades. So for instance, there are tools for coding or generic computer programming, and there are tools that are specific to data science. So what I have right here is a list from the IEEE of the top 10 programming languages in 2015. And it starts at Java and C and goes down to Shell. And some of these are also used for data science. So for instance, Python and R and SQL are used for data science. But the other ones aren't major ones in data science. So let's in fact take a look at a different list of most popular tools for data science. And you see that things move around a little bit. Now R's at the top, SQL's there, Python's there. But for me, what's the most interesting on this list is that Excel is number 5. Which would never be considered programming per se, but is in fact a very important tool for data science. And that's one of the ways that we can compare and contrast computer programming with data science. In sum, we can say this: data science is not equal to coding. They're different things. On the other hand, they share some of the tools and they share some practices, specifically when coding for data. On the other hand, there is one very big difference, and that's statistics. Statistical ability is one of the major separators between general purpose programming and data science programming. When we talk about data science and we're contrasting it with some fields, another field that a lot of people get confused and think they're the same thing is data science and statistics. Now, I'll tell you, there's a lot in common, but we can talk a little bit about the different focuses of each. And we also get into the issue of sort of definitionalism, that data science is different because we define it differently, even when there's an awful lot in common between the two. It helps to take a look at some of the things that go on in each field. So let's start here about statistics. Put a little circle here and we'll put data science. And to borrow a term from Stephen Jay Gould, we can call these non-overlapping magisteria or noma. So you think of them as separate fields that are sovereign unto themselves with nothing to do with each other. But that doesn't seem right. And part of that is if we go back to the data science Venn diagram, statistics is one part of it. There it is in the top corner. So now what do we do? What's the relationship? So it doesn't make sense to say these are totally separate areas. Maybe data science and statistics, because they share procedures, maybe data science is a subset or a specialty of statistics, more like this. But if data science were just a subset or specialty within statistics, then it would follow that all data scientists would first be statisticians. And interestingly, that's just not so. Say, for instance, we take a look at the data science stars, the superstars in the field. We go to a rather intimidating article. It's called The World's 7 Most Powerful Data Scientists from Forbes.com. And you can see the article if you go to this URL. There's actually more than 7 people on the list because sometimes he brings them up in pairs, but let's check their degrees, see what their academic training is in. If we take all the people on this list, we have 5 degrees in computer science, 3 in math, 2 in engineering, and 1 each in biology, economics, law, speech pathology, and 1 in statistics. And so that tells us, of course, that these major people in data science are not trained as statisticians. Only one of them has formal training in that. So that gets us to the next question. Where do these two fields, statistics and data science, diverge? Because they seem like they should have a lot in common, but they don't have a lot in training. And specifically, we can look at the training. Most data scientists are not trained formally as statisticians. Also, in practice, things like machine learning and big data, which are central to data science, are not shared generally with most of statistics. And so they have separate domains there. And then there's the really important issue of context. Data scientists tend to work in different settings than statisticians. Specifically, data scientists very often work in commercial settings where they're trying to get recommendation engines or ways of developing a product that will make them money. So maybe instead of having data science as a subset of statistics, we can think of it more as these two fields have different niches. They both analyze data, but they do different things in different ways. So maybe it's fair to say they overlap. They both have analysis in common of data, but otherwise they are ecologically distinct. So in sum, what we can say here is that data science and statistics both use data and they analyze it, but the people in each tend to come from different backgrounds and they tend to function with different goals and contexts, and in that way render them to be conceptually distinct fields despite the apparent overlap. As we work to get a grasp on data science, there's one more contrast I want to make explicitly, and that's between data science and business intelligence, or BI. The idea here is that business intelligence is data in real life. It's very, very applied stuff. The purpose of BI is to get data on internal operations, on market competitors, and so on, and make justifiable decisions as opposed to just sitting in the bar and doing whatever comes to your mind. Now, data science is involved with this, except, really there's no coding in BI. There's using apps that already exist. And the statistics in business intelligence tend to be very simple. They tend to be counts and percentages and ratios. And so it's simple. The light bulb is simple. It just does its one job. There's nothing super sophisticated there. Instead, the focus in business intelligence is on domain expertise and on really useful direct utility. It's simple, it's effective, and it provides insight. Now, one of the main associations with business intelligence is what are called dashboards or data dashboards. They look like this. It's a collection of charts and tables that go together to give you a very quick overview of what's going on in your business. And while a lot of data scientists may, let's say, look down their nose upon dashboards, I'll say this. Most of them are very well designed, and you can learn a huge amount about user interaction and the accessibility of information from dashboards. So really, where does data science come into this? What's the connection between data science and business intelligence? Well, data science can be useful to BI in terms of setting it up, identifying data sources, and creating or setting up the framework for something like a dashboard or a business intelligence system. Also, data science can be used to extend it. Data science can help get past the easy questions and the easy data to get the questions that are actually most useful to you, even if they require really sometimes data that's hard to wrangle and work with. And also there's an interesting interaction here that goes the other way. Data science practitioners can learn a lot about design from good business intelligence applications. So I strongly encourage anybody in data science to look at them carefully and see what they can learn. In sum, business intelligence or BI is very goal-oriented. Data science perhaps prepares the data and sets up the form for business intelligence, but also data science can learn a lot about usability and accessibility from business intelligence. And so it's always worth taking a close look. Data science has a lot of really wonderful things about it, but it is important to consider some ethical issues. And I'll specifically call this do no harm in your data science projects. And for that, we can say thanks to Hippocrates, the guy who gave us the Hippocratic Oath of do no harm. Let's specifically talk about some of the important ethical issues very briefly that come up in data science. Number one is privacy. That data tells you a lot about people, and you need to be concerned about the confidentiality. If you have private information about people, their names, their social security numbers, their addresses, their credit scores, their health, that's private, that's confidential, and you shouldn't share that information unless they specifically gave you permission. Now, one of the reasons this presents a special challenge in data science, because we'll see later, a lot of the sources that are used in data science were not intended for sharing. If you scrape data from a website or from PDFs, you need to make sure that it's okay to do that, but it was originally created without the intention of sharing. So privacy is something that really falls upon the analyst to make sure they're doing it properly. Next is anonymity. One of the interesting things we find is that it's really not hard to identify people in data. If you have a little bit of GPS data and you know where a person was at 4 different points in time, you have about a 95% chance of knowing exactly who they are. You look at things like HIPAA, that's the Health Insurance Portability and Accountability Act. Before HIPAA, it was really easy to identify people from medical records. Since then, it has become much more difficult to identify people uniquely. That's an important thing for really people's well-being. And then also proprietary data. If you're working for a client, a company, and they give you their own data, that data may have identifiers. You may know who the people are and they're not anonymous anymore. So anonymity may or may not be there. Major efforts to make data anonymous. But really the primary thing is that even if you do know who they are, that you still maintain the privacy and confidentiality of the data. Next, there's the issue about copyright, where people try to lock down information. Now, just because something is on the web doesn't mean that you're allowed to use it. Scraping data from websites is a very common and a useful way of getting data for projects. You can get data from web pages, from PDFs, from images, from audio, from really a huge number of things. But again, the assumption that because it's on the web, it's okay to use it is not true. You always need to check copyright and make sure that it's acceptable for you to access that particular data. Next in our very ominous picture is data security. And the idea here is that when you go through all the effort to gather data, to clean it up and prepare for an analysis, you've created something that's very valuable to a lot of people. And you have to be concerned about hackers trying to come in and steal the data, especially if the data is not anonymous and it has identifiers in it. And so there is an additional burden placed on the analyst to ensure to the best of their ability that the data is safe and cannot be broken into and stolen. And that can include very simple things like a person who was on the project but is no longer, but took the data on a flash drive. You have to find ways to make sure that that can't happen as well. There's a lot of possibilities. It's tricky, but it's something that you have to consider thoroughly. Now, two other things that come up in terms of ethics, but don't usually get addressed in these conversations. Number one is potential bias. The idea here is that the algorithms or the formulas that are used in data science are only as neutral and bias-free as the rules and the data that they get. And so the idea here is that if you have rules that address something that is associated with, for instance, gender or age or race or economic standing, you might unintentionally be building in those factors, which, say, for instance, for Title IX, you're not supposed to. You might be building those into the system without being aware of it. And an algorithm has this sheen of objectivity, and people can say they can place confidence in it without realizing that it's replicating some of the prejudices that may happen in real life. Another issue is overconfidence. And the idea here is that analyses are limited simplifications. They have to be. That's just what they are. And because of this, you still need humans in the loop to help interpret and apply this. The problem is when people run an algorithm, they get out a number, say to 10 decimal places, and they say, this must be true, and treat it as written in stone, absolutely unshakable truth. When in fact, if the data were biased going in, if the algorithms were incomplete, if the sampling was not representative, you can have enormous problems and go down the wrong path with too much confidence in your own analyses. So once again, humility is in order when doing data science work. In sum, data science has enormous potential, but it also has significant risks involved in the projects. Part of the problem is that analyses can't be neutral, that you have to look at how the algorithms are associated with the preferences, prejudices, and biases of the people who made them. And what that means is that no matter what, good judgment is always vital to the quality and success of a data science project. Data science is a field that is strongly associated with its methods or procedures. In this section of videos, we're going to provide a brief overview of the methods that are used in data science. Now, just as a quick warning, in this section, things can get kind of technical, and that can cause some people to sort of freak out. But this course is a non-technical overview. The technical hands-on stuff is in the other courses. And it's really important to remember that tech is simply the means to doing data science. Insight, or the ability to find meaning in your data, that's the goal. Tech only helps you get there. And so we want to focus primarily on insight and the tools and the tech as they serve to further that goal. Now, there's a few general categories we're going to talk about, again, with an overview for each of these. The first one is sourcing or data sourcing, and that is how to get the data that goes into data science, the raw materials that you need. The second is coding. That, again, is computer programming that can be used to obtain and manipulate and analyze the data. After that, a tiny bit of math, and that is the mathematics behind data science methods that really form the foundations of the procedures. And then stats, the statistical methods that are frequently used to summarize and analyze data, especially as applied to data science. And then there's machine learning, ML. This is a collection of methods for finding clusters in the data, for predicting categories or scores on interesting outcomes. And even across these 5 things, even then, the presentations aren't too techie crunchy. They're basically still friendly. And really, that's the way it is. And so that is the overview of the overviews. In sum, we need to remember that data science includes tech, but data science is greater than tech. It's more than those procedures. And above all, that tech, while important to data science, is still simply a means to insight in data. The first step in discussing data science methods is to look at the methods of sourcing or getting data that's used in data science. You can think of this as getting the raw materials that go into your analyses. Now, you've got a few different choices when it comes to this in data science. You can use existing data. You can use something called data APIs. You can scrape web data, or you can make data. We'll talk about each of those very briefly in a non-technical manner. But right now, let me say something about existing data. This is data that already is at hand, and it might be in-house data. So if you work for a company, it might be your company records. Or you might have open data. For instance, many governments, many scientific organizations make their data available to the public. And then there's also third-party data. This is usually data that you buy from a vendor, but it exists and it's very easy to plug it in and go. You can also use APIs. Now that stands for Application Programming Interface. And this is something that allows various computer applications to communicate directly with each other. It's like phones for your computer programs. It's the most common way of getting web data, and the beautiful thing about it is it allows you to import that data directly into whatever program or application you're using to analyze the data. Next is scraping data, and this is where you want to use data that's on the web, but they don't have an existing API. And what that means is usually data that's in HTML, web tables and pages, maybe PDFs, and you can do this either with using specialized applications for scraping data, or you can do it in a programming language like R or Python and write the code to do the data scraping. Or another option is to make data, and this lets you get exactly what you need. You can be very specific and you can get what you need. You can do something like interviews, or you can do surveys, or you can do experiments. There's a lot of approaches. Most of them require some specialized training in terms of how to gather quality data. And that's actually important to remember, because no matter what method you use for getting or making new data, you need to remember this one little aphorism you may have heard from computer science. It goes by the name of GIGO. That actually stands for garbage in, garbage out. And it means if you have bad data that you're feeding into your system, you're not going to get anything worthwhile, any real insights out of it. Consequently, it's important to pay attention to metrics or methods for measuring and the meaning, exactly what it is that they tell you. There's a few ways you can do this. For instance, you can talk about business metrics. You can talk about KPIs, which means key performance indicators, also used in business settings, or SMART goals, which is a way of describing the goals that are actionable and timely and so on. You can also talk about, in a measurement sense, classification accuracy. And I'll discuss each of those in a little more detail in a later movie. But for right now, in sum, we can say this. Data sourcing is important because you need to get the raw materials for your analysis. The nice thing is there's many possible methods, many ways that you can use to get the data for data science. But no matter what you do, it's important to check the quality and the meaning of the data so you can get the most insight possible out of your project. The next step we need to talk about in data science methods is coding, and I'm going to give you a very brief non-technical overview of coding in data science. The idea here is that you're going to get in there and you are going to be king of the jungle, master of your domain, and make the data jump when you need it to jump. Now, if you remember when we talked about the data science Venn diagram at the beginning, coding's up here on the top left. And while we often think about sort of people typing lines of code, which is very frequent, it's more important to remember when we talk about coding or just computers in general, what we're really talking about here is any technology that lets you manipulate the data in the ways you need to perform the procedures you need to get the insight that you want out of your data. Now, there are three very general categories that we'll be discussing here on Data Lab. The first is apps. These are specialized applications or programs for working with data. The second is data, or specifically data formats. There are special formats for web data. I'll mention those in a moment. And then code. There are programming languages that give you full control over what the computer does and how you interact with the data. Let's take a look at each one very briefly. In terms of apps, there are spreadsheets like Excel or Google Sheets. These are the fundamental data tools of probably the majority of the world. There are specialized applications like Tableau for data visualization, or SPSS, a very common statistical package in the social sciences and in business. And one of my favorite, JASP, which is a free open source analog of SPSS, which actually I think is a lot easier to use and replicate research with. And there are tons of other choices. Now, in terms of web data, it's helpful to be familiar with things like HTML and XML and JSON and other formats that are used to encapsulate data on the web, because those are the things that you're going to have to be programming about to interact with when you get your data. And then there are actual coding languages. R is probably the most common, along with Python, a general purpose language, but it's been well adapted for data use. There's SQL, the structured query language for databases, and very basic languages like C and C++ and Java, which are used more in the back end of data science. And then there's Bash, the most common command line interface, and regular expressions. And we'll talk about all of these in other courses here at Data Lab. But remember this, tools are just tools. They're only one part of the entire data science process. They're a means to the end. And the end, the goal, is insight. You need to know where you're trying to go and then simply choose the tools that help you reach that particular goal. That's the most important thing. So, in sum, here's a few things. Number one, use your tools wisely. Remember, your questions need to drive the process, not the tools themselves. Also, I'll just mention that a few tools is usually enough. You can do an awful lot with Excel and R. And then the most important thing is focus on your goal and choose your tools and even your data to match the goal so you can get the most useful insights from your data. The next step in our discussion of data science methods is mathematics, and I'm going to give a very brief overview of the math involved in data science. Now, the important thing to remember is that math really forms the foundation of what we're going to do. If you go back to the data science Venn diagram, we've got stats up here in the right corner, but really it's math and stats, or quantitative ability in general. But we'll focus on the math part right here. And probably the most important question is how much math is enough to do what you need to do? Or to put it another way, why do you need math at all? Because you've got a computer to do it. Well, I can think of 3 reasons you don't want to rely on just the computer, but it's helpful to have some sound mathematical understanding. Here they are. Number 1, you need to know which procedures to use and why. So you have your question, you have your data, you need to have enough of an understanding to make an informed choice. That's not terribly difficult. 2, you need to know what to do when things don't work right. Sometimes you get impossible results. I know in statistics you can get a negative adjusted R squared. That's not supposed to happen. And it's good to know the mathematics that go into calculating that so you can understand how something apparently impossible can work. Or you're trying to do a factor analysis or principal component, you get a rotation that won't converge. It helps to understand what it is about the algorithm that's happening and why that won't work in that situation. And number 3, interestingly, some procedures, some math is easier and quicker to do by hand than by firing up the computer. And I'll show you a couple of examples in later videos where that can be the case. Now, fundamentally, there's a nice sort of analogy here. Math is to data science, as for instance, chemistry is to cooking, kinesiology is to dancing, and grammar is to writing. The idea here is that you can be a wonderful cook without knowing any chemistry. But if you know some chemistry, it's going to help. You can be a wonderful dancer without knowing kinesiology, but it's going to help. And you can probably be a good writer without having an explicit knowledge of grammar, but it's going to make a big difference. The same thing is true of data science. You will do it better if you have some of the foundational information. So the next question is, what kinds of math do you need for data science? Well, there's a few answers to that. Number one is algebra. You need some elementary algebra. That's the basically simple stuff. You can have to do some linear or matrix algebra because that's the foundation of a lot of the calculations. And you can also have systems of linear equations where you're trying to solve several equations all at once. It's a tricky thing to do in theory, but this is one of the things that's actually easier to do by hand sometimes. Now, there's more math. You can get some calculus. You can get some big O, which has to do with the order of a function, which has to do with sort of how fast it works. Probability theory can be important. And then Bayes' theorem, which is a way of getting what's called a posterior probability, can also be a really helpful tool for answering some fundamental questions in data science. So in sum, a little bit of math can help you make informed choices when planning your analyses. Very significantly, it can help you find the problems and fix them when things aren't going right. It's the ability to look under the hood that makes a difference. And then, truthfully, some mathematical procedures, like systems of linear equations, that can even be done by hand, sometimes faster than you can do with a computer. So you can save yourself some time and some effort and move ahead more quickly towards your goal of insight. Now, data science wouldn't be data science and its methods without a little bit of statistics. So I'm going to give you a brief statistics overview here of how things work in data science. Now, you can think of statistics as really an attempt to find order in chaos, find patterns in an overwhelming mess, sort of like trying to see the forest and the trees. Now, let's go back to our little Venn diagram here. We recently had math and stats here in the top corner, and we're going to go back to talking about stats in particular. What you're trying to do here, one thing is to explore your data. You can have exploratory graphics because we're visual people and it's usually easiest to see things. You can have exploratory statistics, a numerical exploration of the data, and you can have descriptive statistics, which are the things that most people would have talked about when they took a statistics class in college, if they did that. Next, there's inference. I've got smoke here because you can infer things about the wind and the air movement by looking at patterns in smoke. The idea here is that you're trying to take information from samples and infer something about a population. You're trying to go from one source to another. One common version of this is hypothesis testing. Another common version is estimation, sometimes called confidence intervals. There are other ways to do it, but all of these let you go beyond the data at hand to making larger conclusions. Now, one interesting thing about statistics is you're going to have to be concerned with some of the details and arranging things just so. For instance, you get to do something like feature selection. That's picking variables that should be included or combinations. And there are problems that can come up. There are frequent problems, and I'll address some of those in later videos. There's also the matter of validation. When you create a statistical model, you have to see if it actually is accurate. Hopefully you have enough data that you can have a holdout sample and do that, or you can replicate the study. And then there's the choice of estimators that you use, how you actually get the coefficients or the combinations in your model. And then there's ways of assessing how well your model fits the data. All of these are issues that I'll address briefly when we talk about statistical analysis at greater length. Now, I do want to mention one thing in particular here, and I just call this beware the trolls. There are people out there who will tell you that if you don't do things exactly the way they say to do it, that your analysis is meaningless, that your data is junk, and you've lost all your time. You know what? They're trolls. So the idea here is don't listen to that. You can make enough of an informed decision on your own to go ahead and do an analysis that is still useful. Probably one of the most important things to think about in this is this wonderful quote from a very famous statistician that says, all models or all statistical models are wrong, but some are useful. And so the question isn't whether you're technically right or you have some sort of level of intellectual purity, but whether you've done something that is useful. That, by the way, comes from George Box. And I like to think of it basically as this, as wave your flag, wave your do-it-yourself flag, and just take pride in what you're able to accomplish, even when there are people who may be criticizing it. Go ahead, you're doing something, go do it. And so in sum, statistics allow you to explore and describe your data. They allow you to infer things about the population. There's a lot of choices available, a lot of procedures, but no matter what you do, the goal is useful insight. Keep your eyes on that goal and you will find something meaningful and useful in your data to help you in your own research and projects. Let's finish our data science methods overview by getting a brief overview of machine learning. Now, I got to admit, when you say the term machine learning, people start thinking about something like the robot overlords who are going to take over the world. That's not what it is. Instead, let's go back to our Venn diagram one more time. And in the intersection at the top between coding and stats is machine learning, or as it's commonly called, is just ML. The goal of machine learning is to go and work in a data space. So you can, for instance, take a whole lot of data. We've got tons of books here. And then you can reduce the dimensionality. That is, take a very large scattered data set and try to find the most essential parts of that data. And then you can use these methods to find clusters within the data, like goes with like. You can use methods like k-means. You can also look for anomalies or unusual cases that show up in the data space. Or if we go back to categories, again, I talked about like for like. You can use things like logistic regression or K nearest neighbors, KNN. You can use naive Bayes for classification, or decision trees, or SVM, which is support vector machines, or artificial neural nets. Any of those will help you find the patterns and the clumping in your data so you can get similar cases next to each other and get the cohesion that you need to make conclusions about these groups. Also, a major element of machine learning is predictions. You're going to point your way down the road. The most common approach here, the most basic, is linear regression, multiple regression. There's also Poisson regression, which is used for modeling count or frequency data. And then there's the issue of ensemble models, where you create several models and you take the predictions from each of those and you put them together to get an overall more reliable prediction. Now, I'll talk about each of these in a little more detail in later courses, but for right now, I mostly just want you to know that these things exist, and that's what we mean when we refer to machine learning. So, in sum, machine learning can be used to categorize cases and to predict scores on outcomes, and there's a lot of choices, many choices and procedures available. But again, as I said with statistics, and as I'll say again many times after this, no matter what, the goal is not that I'm going to do an artificial neural network or an SVM. The goal is to get useful insight into your data. Machine learning is a tool, and use it to the extent that it helps you get that insight that you need. In the last several videos, I've talked about the role in data science of technical things. On the other hand, communicating is also central to the practice. And the first thing I want to talk about there is interpretability. The idea here is that you want to be able to lead people through a path on your data. You want to tell a data-driven story. And that's the entire goal of what we're doing with data science. Now, another way to think about this is when you're doing your analysis, what you're trying to do is solve for value. You're making an equation, you take the data, you're trying to solve for value. The trouble is this: a lot of people get hung up on analysis, but they need to remember that analysis is not the same thing as value. Instead, I like to think of it this way, that analysis times story is equal to value. Now, please note, that's multiplicative, not additive. And so one consequence of that is when you go back to analysis times story equals value, well, if you have zero story, you're going to have zero value because, as you recall, anything times zero is zero. So instead of that, let's go back this and say what we really want to do is we want to maximize the story so that we can maximize the value that results from our analysis. Again, maximum value is the overall goal here. The analysis, the tools, the tech are simply methods for getting to that goal. So let's talk about goals, for instance. Analysis is goal-driven. You're trying to accomplish something in specific. And so the story or the narrative or the explanation you give about your project should match those goals. If you're working for a client and they had a specific question that they wanted you to answer, then you have a professional responsibility to answer those questions clearly and unambiguously so they know whether you said yes or no and they know why you said yes or no. Now, part of the problem here is the fact that the client isn't you and they don't see what you do. And as I show here, simply covering your face doesn't make things disappear. You have to worry about a few psychological abstractions. You have to worry about egocentrism. And I'm not talking about being vain. I'm talking about the idea that you think other people see and know and understand what you know. That's not true. Otherwise, they wouldn't have hired you in the first place. And so you have to put it in terms that the client works with and that they understand. And you're going to have to get out of your own center in order to do that. Also, there's the idea of false consensus, the idea that, well, everybody knows that. And again, that's not true. Otherwise, they wouldn't have hired you. You need to understand that they're going to come from a different background with a different range of experience and interpretation. You're going to have to compensate for that. A funny little thing is the idea about anchoring. When you give somebody an initial impression, they use that as an anchor and then they adjust away from it. So if you're going to try to flip things over on their heads, watch out for giving a false impression at the beginning, unless you absolutely need to. But most importantly, in order to bridge the gap between the client and you need to have clarity and explain yourself at each step. You can also think about the answers. When you're explaining the project to the client, you might want to start in a very simple procedure. State the question that you're answering. Give your answer to that question. And if you need to, qualify as needed, and then go in order top to bottom. So you're trying to make it as clear as possible what you're saying, what the answer is, and make it really easy to follow. Now, in terms of discussing your process, how you did this all, most of the time, it's probably the case that they don't care. They just want to know what the answer is and that you used a good method to do that. So in terms of discussing process or the technical details, only when absolutely necessary. That's something to keep in mind. The process here is to remember that analysis, which means breaking something apart. This, by the way, is a mechanical typewriter broken into its individual components. Analysis means to take something apart. An analysis of data is an exercise in simplification. You're taking the overall complexity, sort of the overwhelmingness of the data, and you're boiling it down and finding the patterns that make sense and serve the needs of your client. Now, let's go to a wonderful quote from our friend Albert Einstein here, who said, "Everything should be made as simple as possible, but not simpler." That's true in presenting your analysis. Or, if you want to go see the architect and designer Ludwig Mies van der Rohe, who said, "Less is more." It's actually Robert Browning who originally said that, but Mies van der Rohe popularized it. Or if you want another way of putting a principle that comes from my field, I'm actually a psychological researcher. They talk about being minimally sufficient, just enough to adequately answer the question. If you're in commerce, you know about a minimal viable product. It's sort of the same idea with an analysis here, the minimum viable analysis. So here's a few tips. When you're giving a presentation, more charts, less text. Great. And then simplify the charts. Remove everything that doesn't need to be in there. Generally, you want to avoid tables of data because those are hard to read. And then one more time, because I want to emphasize it, less text. Again, charts, tables can usually carry the message. And so let me give you an example here. I'm going to give a very famous data set, Berkeley admissions. Now, these are not stairs to Berkeley, but it gives the idea of trying to get into something that's far off and distant. Here's the data. This is graduate school admissions in 1973. So it's over 40 years ago. But the idea is that men and women were both applying for graduate school at the University of California at Berkeley. And what we found is that 44% of the men who applied were admitted. That's their part in green. And that of the women, only 35% were admitted when they applied. So really, at first glance, this is bias, and it actually led to a lawsuit. It was a major issue. So what Berkeley then tried to do is find out, well, which programs are responsible for this bias? And then you got a very curious set of results. If you break the applications down by program, and here we're just calling them A through F, 6 different programs, what you find actually is that in each of these, male applicants are on the left, female applicants are on the right. If you look at program A, women actually got accepted at a higher rate. And the same is true for B. And the same is true for D. And the same is true for F. And so this is a very curious set of responses, and it's something that requires explanation. Now in statistics, this is known as Simpson's paradox. But here's the paradox. Bias may be negligible at the department level. And in fact, as we saw in 4 of the departments, there was a possible bias in favor of women. And the problem is that women applied to more selective programs with lower acceptance rates. Now, some people stop right here and say, therefore, nothing's going on, nothing to complain about. But that's still ending the story a little bit early. There are other questions that you can ask. And as producing a data-driven story, this is stuff that you would want to do. So for instance, you may want to ask, why do the programs vary in overall class size? Why do the acceptance rates differ from one program to the other? Why do men and women apply to different programs? And you might want to look at things like the admissions criteria for each of the programs, the promotional strategies, how they advertise themselves to students. You might want to look at the kinds of prior education students have in each of the programs, and you really want to look at funding levels for each of the programs. And so really you get one answer. It leads to more questions, maybe some more answers and more questions. And you need to address enough of this to provide a comprehensive overview and solution to it for your client. In sum, let's say this: stories give value to data analyses. And when you tell the story, you need to make sure that you are addressing your client's goals in a clear, unambiguous way. And the overall principle here is be minimally sufficient. Get to the point, make it clear, say what you need to, but otherwise be concise and make your message clear. The next step in discussing data science and communicating is to talk about actionable insights, or information that can be used productively to accomplish something. Now, to give sort of a bizarre segue here, you look at a game controller. It may be a pretty thing, it may be a nice object, but remember, game controllers exist to do something. They exist to help you play the game and to do it as effectively as possible. They have a function, they have a purpose. Same way, data is for doing. Now that's a paraphrase from one of my favorite historical figures, and this is William James, the father of American psychology and pragmatism in philosophy. And he has this wonderful quote. He said, "My thinking is first and last and always for the sake of my doing." And the idea applies to analysis. Your analysis and your data is for the sake of your doing. And so you're trying to get some sort of specific insight in how you should proceed. What you want to avoid is the opposite of this from one of my other favorite cultural heroes, the famous Yankees catcher, Yogi Berra, who said, "We're lost, but we're making good time." And so the idea here is that frantic activity does not make up for a lack of direction. You need to understand what you're doing so you can reach the particular goal. And your analysis is supposed to do that. So when you're giving your analysis, you're going to try to point the way. Remember, why was the project conducted? The goal is usually to direct some kind of action, reach some kind of goal for your client, and that the analysis should be able to guide that action in an informed way. One thing you want to do is you want to be able to give the next steps to your client. Give the next steps. Tell them what they need to do now. You want to be able to justify each of those recommendations with the data and your analysis. As much as possible, be specific. Tell them exactly what they need to do. Make sure it's doable by the client, that it's within their range of capability, and that each step should build on the previous step. Now, that being said, there is one really fundamental sort of philosophical problem here, and that's the difference between correlation and causation. Basically, it goes this way. Your data gives you correlation. You know that this is associated with that. But your client doesn't simply want to know what's associated. They want to know what causes something. Because if they're going to do something, that's an intervention. It's designed to produce a particular result. So really, how do you get from the correlation, which is what you have in the data, to the causation, which is what your client wants? Well, there's a few ways to do that. One is experimental studies. These are randomized controlled trials. Now, that's theoretically the simplest path to causality, but it can be really tricky in the real world. There are quasi-experiments, and these are methods, a whole collection of methods, that use non-randomized data, usually observational data, adjusted in particular ways to get an estimate of causal inference. Or there's the theory and experience. And this is research-based theory and domain-specific experience. And this is where you actually get to rely on your client's information. They can help you interpret the information, especially if they have greater domain expertise than you do. Another thing to think about are the social factors that affect your data. Now, you remember the data science Venn diagram. We've looked at it lots of times. It's got these three elements. Some people have proposed adding a fourth circle to this Venn diagram, and we'll kind of put that in there and say that social understanding is also important, critical really, to valid data science. Now, I love that idea, and I do think that it's important to understand how things are going to play out. There's a few kinds of social understanding. You want to be aware of your client's mission. You want to make sure that your recommendations are consistent with your client's mission. Also, that your recommendations are consistent with your client's identity, not just this is what we do, but this is really who we are. You need to be aware of the business context, sort of the competitive environment and the regulatory environment that they're working in, as well as the social context. And that can be outside of the organization, but even more often within the organization. Your recommendations will affect relationships within the client's organization. And you're going to try to be aware of those as much as you can to make it so that your recommendations can be realized the way they need to be. So in sum, data science is goal focused. And when you're focusing on that goal for your client, you need to give specific next steps that are based on your analysis and justifiable from the data. And in doing so, be aware of the social, political, and economic context that gives you the best opportunity of getting something really useful out of your analysis. When you're working in data science and trying to communicate your results, presentation graphics can be an enormously helpful tool. Think of it this way. You are trying to paint a picture for the benefit of your client. Now, when you're working with graphics, there can be a couple of different goals. It depends on what kind of graphics you're working with. There's the general category of exploratory graphics. These are ones that you are using as the analyst. And for exploratory graphics, you need speed and responsiveness. And so you get very simple graphics. This is a base histogram in R, and they can get a little more sophisticated. And this is done in ggplot, and then you can break it down in a couple of histograms, or you can make it a different way, or make them see-through, or split them apart into small multiples. But in each case, this is done for the benefit of you as the analyst understanding the data. These are quick, they're effective. Now, they're not very well labeled, and they're usually for your insight, and then you do other things as a result of that. On the other hand, presentation graphics, which are for the benefit of your client, those need clarity and they need a narrative flow. Now, let me talk about each of those characteristics very briefly. Clarity versus distraction. There are things that can go wrong in graphics. Number one is colors. Colors can actually be a problem. Also, three-dimensional or false third dimensions are nearly always a distraction. One that gets a little touchy for some people is interaction. We think of interactive graphics as really cool, great things to have, but you run the risk of people getting distracted by the interaction and start playing around with it, going like, ooh, I press here, it does that. And that distracts from the message. So actually, it may be important to not have interaction. And then the same thing is true of animation. Flat static graphics can often be more informative because they have fewer distractions in them. Let me give you a quick example of how not to do things. Now, this is a chart that I made. I made it in Excel and I did it based on some of the mistakes I've seen in graphics submitted to me when I teach. And I guarantee you everything in here I have seen in real life, just not necessarily combined all at once. Let's zoom in on this a little bit so we can see the full badness of this graphic. And let's see what's going on here. We've got a scale here that starts at 8, goes to 28%, and it's tiny, doesn't even cover the range of the data. We've got this bizarre picture on the wall. We have no axis lines on the walls. We come down here, the labels for educational levels are in alphabetical order instead of the more logical higher levels of education. Then we've got the data represented as cones, which are difficult to read and compare, and it's only made worse by the colors and the textures. You know, if you want to take an extreme, this one for grad degrees doesn't even make it to the floor value of 8%. And this one for high school grad is cut off at the top at 28%. And this, by the way, is a picture of a sheep, and people do this kind of stuff and it drives me crazy. If you want to see a better chart with the exact same data, this is it right here. It's a straight bar chart. It's flat. It's as simple. It's as clean as possible. And this is better in many ways. Most effective here is that it communicates clearly. There's no distractions. It's a logical flow. This is going to get the point across so much faster. And I can give you another example of it. Here's a chart I showed previously about salaries for incomes. I have a list here. I've got data scientists in it. If I want to draw attention to it, I have the option of like putting a circle around it, and I can put a number next to it to explain it. That's one way to make it easy to see what's going on. But you don't even have to get fancy. You know, I just got out a pen and a Post-it note and I drew a bar chart of some real data about life expectancy. This tells the story as well that there is something terribly amiss in Sierra Leone. But now let's talk about creating narrative flow in your presentation graphics. To do this, I'm going to pull some charts from my most cited academic paper, which is called A Third Voice, a review of empirical research on the psychological outcomes of restorative justice. Think of that as mediation for juvenile crimes, mostly juvenile. And this paper is interesting because really it's about 14 bar charts with just enough text to hold them together. And you can see there's a flow. The charts are very simple. This is judgments about whether the criminal justice system was fair. The 2 bars on the left are victims. The 2 bars on the right are offenders. And for each group on the left are people who participated in restorative justice or victim offender mediation or mediation for crimes. And for each set on the right are people who went through standard criminal procedures. It says court, but it usually means plea bargaining. Anyhow, it's really easy to see that in both cases, restorative justice bar is higher. People were more likely to say it was fair. They also felt that they had an opportunity to tell their story. That's one reason they might think it's fair. They also felt the offender was held accountable more often. In fact, if you go to court on the offenders, that line's below 50%, and that's the offenders themselves making the judgment. Then you can go to forgiveness and apologies. And again, this is actually a simple thing to code, and you can see there's an enormous difference. And in fact, one of the reasons there's such a big difference is because in standard court proceedings, the offender very rarely meets the victim. Now, it also turns out that I need to qualify this a little bit because a bunch of the studies included drunk driving with no injuries or accidents. When we take them out, we see a huge change. And then we can go to whether a person's satisfied with the outcome. Again, we see an advantage for restorative justice. Whether the victim is still upset about the crime, now the bars are a little different. And whether they're afraid of re-victimization, that's over a 2-to-1 difference. And then finally, recidivism for offenders or reoffending. And you see a big difference there. And so what I have here is a bunch of charts that are very, very simple to read, and they kind of flow in how they're giving the overall impression and then detailing it a little bit more. There's nothing fancy here. There's nothing interactive. There's nothing animated. There's nothing kind of flowing in 17 different directions. It's easy. but it follows a story and it tells a narrative about the data. And that should be your major goal with presentation graphics. In sum, presenting, or the graphics that you use for presenting, are not the same as the graphics you use for exploring. They have different needs and different goals. But no matter what you're doing, be clear in your graphics and be focused in what you're trying to tell. And above all, create a strong narrative that gives a different level of perspective and answers questions as you go to anticipate a client's question and to give them the most reliable, solid information and the greatest confidence in your analysis. The final element of data science and communicating that I wanted to talk about is reproducible research. And you can think of it as this idea. You want to be able to play that song again. And the reason for that is data science projects are rarely one and done. Rather, they tend to be incremental, they tend to be cumulative, and they tend to adapt to the circumstances that they're working in. So one of the important things here, probably if you want to summarize it very briefly, is this: show your work. There's a few reasons for this. You may have to revise your research at a later date, your own analyses. You may be doing another project and you want to borrow something from previous studies. More likely, you'll have to hand it off to somebody else at a future point, and they're going to have to be able to understand what you did. And then there's the very significant issue in both scientific and economic research of accountability. You have to be able to show that you did things in a responsible way and that your conclusions are justified. That's for clients, funding agencies, regulators, academic reviewers, any number of people. Now, you may be familiar with the concept of open data, but you may be less familiar with the concept of open data science, and that's more than open data. So for instance, I'll just let you know that there is something called the Open Data Science Conference at odsc.com, and it meets 3 times a year in different places. And this is entirely, of course, devoted to open data science, using both open data, but making the methods transparent to people around them. One thing that can make this really simple is something called the Open Science Framework, which is at osf.io. It's a way of sharing your data and your research with an annotation of how you got through the whole thing with other people. It makes the research transparent, which is what we need. One of my professional organizations, the Association for Psychological Science, has a major initiative on this called Open Practices, where they are strongly encouraging people to share their data as much as is ethically permissible and to absolutely share their methods before they even conduct the study as a way of getting rigorous intellectual honesty and accountability. Now, another step in all of this is to archive your data, make that information available, put it on the shelf. And what you want to do here is you want to archive all of your data sets, both the totally raw before you did anything with a data set and every step in process until your final clean data set. Along with that, you want to archive all of the code that you used to process and analyze the data. If you used a programming language like R or Python, that's really simple. If you used a program like SPSS, you need to save the syntax files, and then it can be done that way. And again, no matter what, make sure to comment liberally and explain yourself. Now, part of that is you need to be able to explain your process, because you're not just this lone person sitting on the sofa working by yourself. You're with other people, and you need to explain why you did it the way that you did. You need to explain the choices, the consequences of those choices, the times that you had to backtrack and try it over again. This all also works into the principle of future-proofing your work. You want to do a few things here. Number one, the data. You want to store the data in non-proprietary formats like a CSV or comma-separated values file, because anything could read CSV files. If you stored it in the proprietary SPSS.save format, you might be in a lot of trouble when somebody tries to use it later and they can't open it. Also, there's storage. You want to place all of your files in a secure, accessible location like GitHub. It's probably one of the best choices. And then the code, you may want to use something like a dependency management package like PackRat for R or virtual environment for Python as a way of making sure that the packages that you use, that there are always versions that work, because sometimes things get updated and it gets broken. This is a way of making sure that the system that you have will always work. Overall, you can think of this too. You want to explain yourself, and a neat way to do that is to put your narrative in a notebook. Now, you can have a physical lab book. but you can also do digital books. A really common one, especially if you're using Python, is Jupyter with a Y there in the middle. The Jupyter notebooks are interactive notebooks. So here's a screenshot of a very simple one I made in Python. And you have titles, you have text, you have the graphics. If you're working in R, you can do this through something called R Markdown, which works in the same way. You do it in RStudio, use Markdown, and you can annotate the whole thing. Get more information about that at rmarkdown.rstudio.com. And so for instance, here's an R analysis I did, and you see the code on the left and you see the Markdown version on the right. What's neat about this is that this little bit of code here, this title and this text and this little bit of R code then is displayed as this formatted heading, as this formatted text, and this turns into the entire R output right there. It's a great way to do things. And then if you do R Markdown, you actually have the option of uploading the document into something called RPubs. And that's an online document that can be made accessible to anybody. Here's the same document. And if you want to go see it, you can go to this address. It's kind of long, so I'm going to let you write that one down yourself. But in sum, here's what we have. You want to do your work and archive the information in a way that supports collaboration. Explain your choices, say what you did, show how you did it. This allows you to future-proof your work so that it will work in other situations and for other people. And as much as possible, no matter how you do it, make sure to share your narrative so people understand your process and they can see that your conclusions are justifiable, strong, and reliable. Now, something that I've mentioned several times when talking about data science, and I'll do it again in this conclusion, is that it's important to give people next steps. So I'm going to do that for you right now. If you're wondering what to do after having watched this very general overview course, I can give you a few ideas. Number one, maybe you want to start trying to do some coding in R or Python. We have courses for those. You might want to try doing some data visualization, one of the most important things that you can do. You may want to brush up on statistics and maybe some math that goes along with it. And you may want to try your hand at machine learning. All of these will get you up and rolling in the practice of data science. You can also try looking at data sourcing, find the information that you're going to do. But no matter what happens, try to keep it in context. So for instance, data science can be applied to marketing and sports and health and education and the arts and really a huge number of other things. And we will have courses here at datalab.cc that talk about all of those. You may also want to start getting involved in the community of data science. One of the best conferences that you can go to is O'Reilly Strata, which meets several times a year around the globe. There's also Predictive Analytics World, again, several times a year around the world. Then there's much smaller conferences. I love Tapestry, or tapestryconference.com, which is about storytelling in data science. And Extract, a one-day conference about data stories that's put on by Import.io, one of the great data sourcing applications that's available for scraping web data. If you want to start working with actual data, a great choice is to go to Kaggle.com. And they sponsor data science competitions, which actually have cash rewards. But there's also wonderful data sets you can work with there to find out how they work and compare your results to those of other people. And once you're feeling comfortable with that, you may actually try turning around and doing some service. Datakind.org is the premier organization for data science as humanitarian service. They do major projects around the world. I love their examples. There are other things you can do. There's an annual event called Do Good Data. And then datalab.cc will be sponsoring twice a year Data Lab charrettes, which are opportunities for people in the Utah area to work with local nonprofits on their data. But above all of this, I want you to remember this one thing. Data science is fundamentally democratic. It's something that everybody needs to learn to do in some way, shape, or form. The ability to work with data is a fundamental ability, and everybody would be better off by learning to work with data intelligently and sensitively. Or to put it another way, data science needs you. Thanks so much for joining me for this introductory course. I hope it's been good. and I look forward to seeing you in the other courses here at datalab.cc. Welcome to Data Sourcing. I'm Barton Polson, and in this course, we're going to talk about data opus, or that's Latin for data needed. The idea here is that no data science, and that is a sad thing. So instead of leaving it that, we're going to use this course to talk about methods for measuring and evaluating data, and methods for accessing existing data, and even methods for creating new custom data. Take those together, and it's a happy situation. At the same time, we'll do all of this still at an accessible, conceptual, and non-technical level, because the technical hands-on stuff will happen in later other courses. But for now, let's talk data. For data sourcing, the first thing we want to talk about is measurement. And within that category, we're going to talk about metrics. The idea here is that you actually need to know what your target is if you want to have a chance to hit it. There's a few particular reasons for this. First off, data science is action-oriented. The goal is to do something as opposed to simply understand something, which I say as an academic practitioner. Also, your goal needs to be explicit, and that's important because the goals can guide your effort. So you want to say exactly what you're trying to accomplish so you know when you get there. Also, goals exist for the benefit of the client. They can prevent frustration. They know what you're working on. They know what you have to do to get there. And finally, the goals and the metrics exist for the benefit of the analyst because they help you use your time well. You know when you're done, you know when you can move ahead with something, and that makes everything a little more efficient and a little more productive. Now, when we talk about this, the first thing you want to do is try to define success in your particular project or domain. Depending on where you are in commerce, that can include things like sales or click-through rates or new customers. In education, it can include scores on tests. It can include graduation rates or retention. In government, it can include things like housing and jobs. In research, it can include the ability to serve the people that you're trying to better understand. So whatever domain you're in, there will be different standards for success, and you're going to need to know what applies in your domain. Next are specific metrics or ways of measuring. Now, again, there are a few different categories here. There are business metrics. There are key performance indicators or KPIs. There are SMART goals. That's an acronym. And there's also the issue of having multiple goals. I'll talk about each of those for just a second now. First off, let's talk about business metrics. If you're in the commercial world, there are some common ways of measuring success. A very obvious one is sales revenue. Are you making more money? Are you moving the merchandise? Are you getting sales? Also, there's the issue of leads generated, new customers or new potential customers, because that then in turn is associated with future sales. There's also the issue of customer value or lifetime customer value. So you may have a small number of customers, but they all have a lot of revenue, and you can use that to really predict the overall profitability of your current system. And then there's churn rate, which has to do with losing and gaining new customers and having a lot of turnover. So any of these are potential ways of defining success and measuring it. These are potential metrics. There are others, but these are some really common ones. Now, I mentioned earlier something called a key performance indicator or KPI. KPIs come from David Parmenter, and he's got a few ways of describing them. He says a key performance indicator for business, number one, should be non-financial. So not just